Hi everyone, and welcome back to tutorial number 5. In this tutorial and moving forward, we're going to start looking at experimental designs. So up until this point, we've been looking at observational or correlational designs, where we were interested in the relationship between two numeric variables. In experimental designs, what we're actually interested in now is whether or not changing some factor leads to a different kind of score on a dependent variable. So this is primarily categorical IVs that we're now going to be dealing with. For today's study, we've got quite an interesting design that we're looking at. We have one categorical IV with 4 levels, which is different amounts of soy that people ate, or that men ate throughout their week. And then we have one numeric dependent variable, which is how much sperm a man has. And the idea here is we want to know whether or not changing the amount of soy that a man eats will lead to a different amount of sperm that they have. So we have 3 different research questions or hypotheses that we're interested in. The first is whether or not males who did not eat any soy at all, do they have significantly higher sperm counts than those who ate 1 meal per week with soy in it? Our second hypothesis or research question is, do males who do not eat any soy have significantly different sperm counts to those who ate 4 meals per week with soy? And then finally, do males who did not eat any soy have significantly different sperm to those who ate 7 meals per week with soy? Now, there's something interesting to note here. In all 3 of these, they all start the same. Do males who did not eat soy have significantly blank? And they all generally end the same. Sperm counts from those who ate 1, 4, or 7 meals. But there is one word that is different. In our first hypothesis, we have the word higher. And then after this, we just have different. For the first one, we're specifically asking if eating no soy at all produces higher sperm than those who only ate 1 meal of soy per week. There's an exact direction that we're after. In others, we don't really care if those who ate soy had less sperm than those who ate 1 soy meal per week. We're specifically targeting whether or not there is a higher difference. And so there's a very specific thing we're going to do to target that later on. The other 2 hypotheses just say different. They don't specify higher or lower. So in which case, eating no soy, if that produces higher sperm counts than those who ate 4 soy meals per week, that's just as interesting now to if they're eating no soy produces less sperm. So here we have direction in our first hypothesis, but in our other 2 we don't. And we'll see in a moment why that's important. Moving on, now that we've talked about our hypotheses and the design, we need to consider our sampling population. Now this is taken straight from the guide that you guys have. And it states that we gathered sperm samples, measured in millions per milliliter, from 4 different male participants, after 1 year of a diet that varied in the number of meals containing soy each week. That should have an N in it. So if we now think about the data summary, we have 2 different data sets that we're working from. One called Soy SP and the other one called Soy. Now, Soy SP is what we call a wide format data set, and Soy is what we call a long, and I'll talk about what that is in a second. In both of these, we have one dependent variable, its sperm count. Now, the thing that's different about a wide format dataset to a long format dataset is if our data is long, what this means is that we will have a column in our dataset for our dependent variable scores. And we'll have a column for our categorical variable. And in that column, we'll have the number of which group a person was in. If we're looking at a wide data set, though, what's actually going on is each level of our categorical IV is represented as a separate column in our data set. And then our dependent variable scores are inside each of those columns. So what this means is our dependent variable in our soy SP dataset doesn't actually have a column of its own. The scores for the sperm count are actually within the IV columns. So we have our one IV variable, it's the number of soy meals per week that were consumed. I've got a note here that this is represented in wide format. It's categorical and technically it's ordinal. So what this means is that as we move up in levels, we're increasing in the number of meals. So there's a relationship between the number of the level and the quality of the categorical variable, what's happening. That's different to, say, a nominal variable where the order doesn't matter. So with a nominal variable, let's say it's eye color, I could have blue eyes, green eyes, brown eyes, I could have green, brown, blue. Changing the order doesn't change anything. But here we have an ordinal variable, and what this means is if I was to move level 1 to level 3 to level 2, or something else like that, I will lose the story that I get from this particular order here, which is as I increase in level, I increase in the number of soy meals. For the purposes of this unit, that's all you need to understand, just being able to identify nominal from ordinal, and that's as far as you have to take it. We have 4 levels of this categorical IV, and it's between subjects, which means people are allocated to one type or one amount of soy meals per week. As I was saying before, this is wide format, and what this means is that each of these levels are represented as a separate column in our dataset. So our first level, which is no soy meals per week, is labeled as no soy in our dataset. Level 2 is 1 soy meal per week, and it's called 1 soy. Level 3 is 4 soy meals, and it's called 4 soy. Level 4 has 7 soy meals, it's called 7 soy. So let's go and look at this dataset so we can talk about exactly what's going on here. If we look over here, you can already see that I have 4 variables, each one representing one of the levels of my of my IV. If I open up my data view, inside each of these I can see different scores. These scores represent the sperm counts of the men. So if we were to load up our soy dataset, what we would notice is that there is a slightly different structure to the data. Now we have a variable called smeal and a variable called spcount. If we go into our data browser, what we can see is smeal is a categorical variable, and we know this because it has, first of all, string labels, so in other words it has words, but they're also in blue. And the fact that these words are in blue tells us that there's actually a number underlying each of them. If we're curious what that is, we can right-click, go Data, Value Labels, Hide All Labels, and now we can see that there is a 1 here, and then we have 2s, 3s, and 4s. And then we can do the same process to remove that. And so next to each of these, we can see the sperm count for that particular person. So when our categorical variable is stacked like this, where we have all of group 1, all of group 2, all of group 3, all underneath each other, identified with a numeric, with some number that has a label attached to it, and then we have a separate column with the dependent variable score, we call this a long data set, because it's much, much longer than having each column representing a different IV, or a different level of the IV. However, in a wide data set, we call it wide because it's much wider than if we stack the levels of the IV like this in a long structure. But we're starting with the wide data set, so let's switch back. And we can see we have the wide data set now. So again, in our wide data set, we have 4 columns representing our 4 IVs. But in our long data set, we have a DV, which has its own variable, its own column called spcount. And then our IV, the number of soy meals per week, is labeled smeal. It's still categorical, it's still ordinal. It still has 4 levels and it's still between subjects. But now a score of 1 on smeal represents no soy meals, a score of 2 is 1 soy meal, a score of 3 is 4 soy meals, a score of 4 is 7. So it doesn't matter which way you look at this data set, it's still the same data. The different structures allow for different kinds of analyses. That's the only thing. And we'll need both today. So if we bring all this information together, the first thing we can ascertain is it's an experimental design. And we know this for two reasons. One, we are manipulating the amount of soy consumed. And two, because I told you at the start that we're now looking at experimental designs. The research question involves comparing more than two levels of one categorical IV together. But our hypotheses are specifically comparing two at a time. Our DV is numeric and our IV is categorical. So Anova, specifically one-way Anova, is the most appropriate hypothesis test. So a one-way Anova is simply an analysis that compares two or more groups together on some numeric DV. And it asks the question whether or not the mean DV score for a particular group is different to any other group that you have. This should be sounding somewhat familiar. It should be sounding a little bit like T-Test, particularly independent samples T-Test. We're asking if the mean of the dependent variable for one group is different to the mean dependent variable score for another group. And technically, our research questions are the comparison of two groups together. So we could cheat and just run 3 T-tests, right? So as a reminder, independent samples T-test is when we have categoric between subjects data like we have here. The null hypothesis for a T-test, for an independent samples T-test, is that the mean dependent variable score for group 1 will be the exact same as the mean dependent variable score for group 2. Now, before I was talking about whether or not we have direction in our hypotheses, and this is important for the T-test, because in our T-test we're going to get 3 different p-values. 2 of them are going to be what we call one-tailed T-tests, and the others are two-tailed. Now, one-tailed T-test is a directional T-test, and essentially what this is doing is it's taking our 0.05, our definition of significance, and in a one-tailed T-test, it's giving all of that 0.05 to the direction that we expect. So if we're saying that mean 1 will be higher than mean 2, then all of our 0.05 will be banked onto the T-test directly comparing mean 1 being higher than mean 2. If we expect mean 1 to be less than mean 2, then it will bank the entire 0.05 on mean 1 being less than mean 2. However, if we don't have direction, we run what's called a two-tailed test. And this cuts our 0.05 down the middle and actually gives 0.025 as the significance cutoff for each direction, and it's tested together. So they are slightly different tests in terms of the p-value that you're using to define significance. You don't need to actually adjust your 0.05, you still check against 0.05. Stata's doing all the magic in the background. But it's just important to know that what's happening is Stata is changing the significance value and the test scores. Now, T-tests have 3 assumptions, or independent samples T-tests have 3 assumptions. The first is that the dependent variable is normally distributed at each level of the IV. We can use descriptive, Shapiro-Wilk histograms to do this. There's also the assumption of equality of variance. This is also known as homogeneity of variance. And this is within the DV, within each level of the IV. So essentially all this is saying is that the standard deviation of the DV at one level of the IV is the same as the other level of the IV. We want the standard deviations to be about the same. We use the Levine's test for this. And then independence of error is simply, for the purposes of this course, mean that you haven't measured anyone twice, and this is met by design.